Hi, this is ET250, lecture 13. Last lecture we covered RC circuits, and this lecture we're going to cover RL circuits. We're going to look at just a resistive circuit to first get some intuition on a basic, simple system, and then we'll look at RL, or resistance inductance plots, and see if we can get intuition on these type of circuits. We'll look at the time constant for a RL circuit, and it's L over R as opposed to RC for a resistor capacitor. And then we'll define our transition conditions. Before and after transition can be considered the 0, minus, and 0 plus, or more generally the minus and the plus. And for an inductor, the inductance current cannot jump instantaneously. Same with the capacitance voltage, right? And so that's what these two equations mean. Okay, then we'll kind of just write down what this first order transient process is so that you have a kind of a standard operating procedures for solving these kind of problems. And we'll do an example. Okay, so why don't we get started? So let's just look at a resistive plot. Very simple, switch open, constant voltage source, resistor current, VR. Let's say the switch closes at t equals 0. So initially no current, closes, and we know what happens. Ohm's law kicks in, V equals IR. And we get a very simple plot, right? The current steps up and the voltage steps up, okay? And this shouldn't be any problem. Now, when we add inductance, remember inductance are modeling as a water wheel, it doesn't like that change of state. And so it takes some time for that current to spool up. And so if we have a similar system, resistor, inductor, and we can even give it some numbers like 10 volts, 3 ohms, 0.2 henries. And we can do the same thing. What we'll expect is that the current won't just slam up. The current will take some time, right? And then finally it settles out to the steady state value of the Vs over R, right? And this is going to be from your Ohm's law. In the steady state, this behaves like a short, right? And so you have KVL, VR equals Vs, Ohm's law, Vs equals IR, and so the I equals Vs over R. If you look over here, it's the same thing. Once this slams shut, the voltage is, or the current is Vs over R. Now, what does the voltage look like? Now, remember, this doesn't like a change of state. So it's going to initially provide a pressure or voltage at VL to fight that current. So if I have 0 current, and if I have Vs and the switch is closed, this temporarily has to slam up to Vs, match this voltage to negate any current, but then give way. And so what you're going to see is something like this, where it goes slams up, jumps to Vs initially, but then decays to 0. Okay, and so this is what we would expect. Notice the voltage in an inductor can jump, but the current can't. Okay, all right. So why don't we look at a simulation to see these behavior, and then we'll go in and analyze the math and make sure the math and the simulation match. Okay, so we can go here. I'm going to switch over to my computer, and let's go here. Okay, so if we look at the simulation here, what do we notice? We notice a resistive circuit, and we know a resistive and inductive circuit. And so in this case, if I close the switch, you can watch the current and voltage here on these left oscilloscopes. What do we get? We get a nice DC current, the voltage and current in the resistor slam up, step response, no problem. Okay. Now let's say we go over here to the inductor side, and on the inductor side, I have wired up a current ammeter, a voltage of the resistor, and a voltage of the inductor. Same thing where I have a switch. And remember, the current should take some time to spool up. The voltage of the resistor will respond immediately or in sync with the current, but the voltage of the inductor is going to spike up and decay away. And let's see what we have. Sure enough, we have the voltage of the inductor spike up and decay away. The resistor, current, and voltage are in sync, they're in phase, and you can see it takes time for the current to spool up. Okay, we can do that again. So do like this, shut everything down, and then what happens if we wait for it to steady out? So back to 0, and bang. And you can see again that voltage in the inductor spikes up and the current takes some time to spool up. Okay, so let's go back to the document cam and let's let's just do some analysis on this and see if we can build some intuition and confirm that the theory and our intuition match. Okay, so um, let's look at this system when the switch is closed. And so now we can start redrawing it a little with the switch closed, and we can start applying our first month principles. So Ohm's law, yep, V equals IR. Our inductor equation, VL equals L di dt, yep, and it's a positive version, Okay, what else? Maybe a KVL, yep, minus VS plus VR plus VL equals 0. And just like in the RC circuits, you can start bringing things together. So IR goes in here, LDIL goes in here. We get this. If you notice this, what do we see? First order differential equation. We have the current I and its derivative in the same equation. Well, we know how to solve these now. What do? We can use our guess. We know that this current is going to have, right, this shape, and that's going to be what describes that shape? An exponential, an e to the x kind of shape. And so if we want to be general, k1 e to the st plus k2, right? K2 is going to be that shift. K1 is like related to the initial value. S is the kind of the steepiness of this decay rate or rise rate. We also need the derivative. This is easy, sk1 e to the st, and we're going to plug it in. Okay, once we plug it in, we're going to be able to solve for two of these three unknowns. Okay, so I'm going to rewrite it minus Vs, K1 e to the st plus K2R plus L Sk1 e to the st. Good. So now I have two equations, even though I only have one, and the sneaky two equations are what? The ones attached to the e to the st and the ones without. Okay, so this is what we got to be careful here. The ones attached to the e to the st, you might be tempted to just write K1, but there's a sneaky R over here. So you have to put K1 times R, don't forget that. And then LSK1, good. So now the K1s cancel, and so the LS can go the other side with a minus, and then S equals negative R over L. Good, so that's the S part. That's this part here. Okay, so that's related to the time constant, the rise time of this. Okay, what else do we get from this equation? We have no E to the st on this Vs, and look at this, K2 times R, again, don't forget that R, and then we have nothing over here, okay? So now we have minus Vs plus K2R equals 0, and you can see that this K2 unknown is Vs over R. Look at that, do you see how K2 is gonna be related to this guy over here? Okay, we've got two of the three of these unknowns. We got to do one more, and I'm sure the boundary conditions are going to help. What are going to be the boundary conditions? Well, that's the current or voltage at 0 time or infinite time, right? The boundaries, right? So what's the boundaries in this case? Well, the current here is going to be probably 0, right? Okay. Now, the voltage, yes, before 0 or before the switch closed, we call that 0 minus. Yes, the current voltage are both 0, but right after, the current has to be 0. The current in an inductor, that's just the physical properties of the inductor. You got to remember this, that the current in an inductor cannot instantaneously jump, even though the voltage can, right? So the voltage, and we do see that, the voltage spikes up. So if you know the current before transition of inductor, this is the bridge. You would know the current right after the transition, 0 minus to 0 plus, okay? And so I have it defined here. The minus is just before transition when the switch was still open, and plus is just after the transition when the switch closes. Okay, so let's take this back. The current just after the switch closes is 0 amps. Okay, maybe we'll just even put a little 0 amps here. And we can now plug that into our general form here. We know K2, we know S. Now we're looking for K1. So I'm going to put the 0 in here and the 0 over there. And I have K1 equals negative Vs over R because we found K2 was Vs over R. Okay, good. That's it. That is our expression. So the current is minus Vs over R e to the minus R over Lt plus Vs over R. Okay. We can punch in the numbers so that we can get a numerical result, but the idea is the same. And we can plot this. Well, what would this look like? We know this is an exponential. It has a negative exponential here. At 0 time, this becomes 1. So you have negative 10 thirds plus 10 thirds. Oh, that's nice. 0 current. at 0 time. Good. What happens as this time goes to infinity? As this time goes to infinity, you have a negative infinity. E to the minus infinity goes to 0. So this whole thing wipes out to 0, and you're left with 10/3 of an amp, Vs over R. That's exactly what we predicted, and we should see something like this. Okay. Here in my notes, I have it broken down. If just other ways to look at it, right? This would be positive Vs over R e to the minus RL. If you flip the negative, you would have this, and you flip the negative plus a constant, you would shift it up. Another way to think about how to plot it, but all consistent. Okay. So this is the final current plot, which matched our simulation and matched our predicted result. Okay, good. So what if the question asks, what's the inductor voltage, right? So we go back here and we ask, what is the inductor voltage as a function of time, right? What's that guy? Well, we know that the inductor voltage is related to the current by a derivative, and we can use this equation. Oh, nice. We have I, we know L. Do you know how to take the derivative of this? We totally do. The derivative of this is the derivative of that, right? They're the same thing. This is just the symbolic result. This is the numerical. Let's do symbolic first, and then we'll punch in the numbers. That way we can see where everything's coming from. The derivative of this, okay, let's be very careful. It's minus RL over L comes to the front. That's it. And then this goes away. Oh, that was easy. Okay, minus minus becomes a positive. R's cancel. So you get Vs over L, e to the minus R over LT. That is your derivative equation, right? And the derivative equation multiplied by L is going to give you VL, because this is just the IDT. Notice that's nice because these L's cancel. Okay, because that way you're left with units of voltage. So it's kind of nice to do it symbolically sometimes so that you can see that your units, if I just did it from here, you might not get the satisfaction that L canceled, right? Because this looks weird. What's a V over L, right? Well, technically V over L is a dIdt, but it might not be clear that you're going to end up in units of volts. All right, so we have the voltage equals Vs e to the minus R over LT in terms of a symbolic result. We can plug in the numbers, and what do we get? Well, we know that the voltage of the inductor was 0 initially, but it spikes up and then decays, right? We know what this looks like. It starts at 10, right? And then decays at this rate. Okay, and this is exactly what we saw. So this is nice. We have the theoretical result from just crunching the math blindly. We have our intuition, and we can see it in the simulation. So this is very nice. Again, the time constant is the time to get to e to the minus 1, right? In this case, it's going to be L over R. I hope you guys can see that, right? To get this to be a 1 in the exponent, I have L over R as my time constant, right? And I have that rewritten here. So you can see the time constant, the time it takes to get to a 1 in here is going to be L over R. Very good. Okay, and then again, this is units of seconds. And let's remind yourselves, what does the time constant mean? It's the time to get to within 63% of the final value. So here, the time constant is about here. So to get 63% of the final value, in this case, is 0 volts. Here for the current, to get to within 63% of Vs over R. Okay, so again, it's just the metrics. This was just a way to show that numerically you get to the 63%. E to the minus 1 is 0.368, but when I add in that extra factor here, I'm going to get that 0.63 because you have the minus here, okay? So pause the video if that's a little unclear and just work that out for yourself. But otherwise, let's keep going. We can check the units. We can make sure that L over R has units of time, just like when we checked RC has units of time. Well, an L over R has henries and ohms. A henry is a volt second per amp, and an ohm is a volt per amp. We can plug that in, okay? Amp second per volt and amp per volt, right? And what do we have here? We have amps per volts cancel, and we get seconds. Is this correct? Let's double check that. A henry equals, let's see, amp second, yep. So it's a volt second per amp. I think I might have had my derivation wrong. And V equals IR is a, ohms over here is a volt per amp, right? And so I think I switched the volts and amps here. And let's double check. So that's a volt second per amp on the top, and then this is a volt per amp on the bottom. You still get that same cancellation. This is incorrect. This should be a volt second per amp, and this is a volt per amp. You know, sometimes I make mistakes too. I apologize for that. But still, we get the nice cancellation here, and we're left in seconds. Got lucky. Whew. Let's keep going. All right, so what do we have here? I want to highlight the transition conditions. I mentioned before that the current in an inductor can't jump. So let's just be explicit. If you have an inductor, the current before the transition must equal the current after the transition. The current can't jump in an inductor. It can jump in a resistor. It can jump in a capacitor, but it can't jump in an inductor. Okay. All right. What about a capacitor? Well, if you have a capacitor, it's the voltage that can't jump. Again, remember this duality, right? Whatever the capacitor is, the inductor is like the opposite, right? So the voltage can't jump, but the current can. And why? It's based on the physics. Here you have the inertia, the water wheel inertia doesn't like to have that instantaneous change in current. Here you have that spring, it doesn't like an instantaneous change in pressure. It'll deflect really quick, but it won't have that instantaneous change in pressure, okay? And 0 minus is before and after the transition. Now, technically, it doesn't have to be at 0 time. It could have been at 3 seconds, 4 seconds, 10 seconds, okay? So the minus and plus is really what you care about before and after a transition, okay? All right, let's keep moving. So here I want to clearly delineate the process for these first order differential equations. So the first thing you want to do is kind of identify these boundary conditions. Let's say you have a transition. You want to know whatever element you're looking at. What's the current before and voltage before transition? And what's the current or voltage after the transition? And here, depending on if it's a capacitor or inductor, you might say these are equal or these are equal. Then over here, after in your transient condition, you might go, oh, okay, this we know is going to be where we're all the first order differential equation process. But if we're looking for the boundary conditions, we might fast forward and look at what happens as time goes to infinity. Okay, so as time goes infinity, we might want to know, well, what's the current and voltage at? These could be boundary conditions that you could use to plug in and solve for the K1, right? Okay, once you've identified the boundary conditions, what you also would want to do is draw an intuitive plot, like have a mental image of what the current and voltages are going to do before you even crunch the math. And the boundary conditions will help you kind of locate the plot. Okay, then, all right, now we start grinding, right? Now you're going to use the KVL, you're going to close the switch, you're going to analyze it during this transient time, you're going to apply your KVLs, your KCLs, your Ohm's law, your capacitor inductor equations, and you're going to get a first order differential equation. Once you get a first order differential equation, you go, okay, no problem. I know how to solve that. I can apply my guess. Whatever voltage or current I'm looking for, I can say the current or voltage equals K1 EVST plus K2, where these are unknown. And the derivative is K1S EVST. Again, these three are unknowns. Okay, I take this and I plug it back into my first order equation, and I need to get the three unknowns solved. I can only get two of the three because I only get two equations out of here. And then I need to use these boundary conditions to get that third unknown, okay? Once I get these unknowns, I'm done. I just plug it back into my guess, and then I have a plot. I can plot whatever I want, okay? So I hope this is not a too bad, 7 steps here, and really the meat is kind of like this. So not too bad. So why don't we do one more example? This is a tricky example, but I think the trickier the examples are, the better for understanding, okay? As long as you can keep up. Let's look at this example here. So what do we have? We have a voltage source, a resistor, 1, 2, and 3, an inductor, and we have two currents, IL and I. So don't get confused with IL and I. We have the voltage across the inductor labeled, and this time we're starting with the switch closed, and we're going to open it to equal 0 seconds, okay? They give us all the values for the voltages and inductance and resistances, and they want us to plot these three entities. So not just the current and voltage for the inductor, but also this current as well. Okay, so when this is closed, we'll say it's steady state. When this is in steady state, the inductor behaves like a short. So it's like a wire. So the voltage is going to be 0. These two currents are not going to be 0. You can imagine current's going to leave this and flow into both via a current divider kind of situation. So you're getting non-zero steady state current when this switch is closed. Okay. When I open it, what happens? This left part of the circuit is gone, and now this inductor will have current through it. It's going to want to not change its state. So it's going to try to keep current flowing in this direction, right? And what's going to happen? Eventually, it'll burn out on these two resistors, okay? So let's try to imagine what's going to happen. Steady state, current's flowing down in both branches. Switch opens, the current in this branch immediately flips to the other side because now these two are in series, and this inductor is going to overpower and keep current swirling in this direction. So IL will stay positive and I will flip negative, okay? What's VL going to do? Well, initially VL is 0, and then the second that, boom, this switch opens, this is acting like a battery with the positive polarity here sending current this way. So you're going to see VL spike to a negative number and decay. And let's see if we can do some analysis to figure all this out. Okay, so let's just look at the steady state condition first. So we have the steady state where the inductor is essentially gone, right? Acting like it's short. All right, so this is like a week 1, month 1 homework problem now. 3 resistors, 2 in parallel, IL, IS, VS. I put an IS here just to help myself because I want to use current divider. IL equals IS times R3 over R2 plus R3, good. And if we also say, well, if I don't know IS, we can solve for it by crunching this down and doing a little Ohm's law on this, okay? So if I crunch this down, this is an R equivalent, R2, R3 over R2 plus R3, no problem. And then what? I can combine these, and my current here is going to be the Ohm's law of this, right? And these two are in series, no problem. So once I have IS, I know it's 3 amps, I can plug it into here, and then once I have this, I can get IL. Don't forget, this is just the steady state, right? This is just before we've even opened the switch. But notice how our fundamentals from the month 1 don't go away. We still need our tools. Okay, so I plug it back into the current divider. I know I did this symbolically, right? Okay, and I did it symbolically so you can see where all the symbols come from. Don't get lost in the sauce, please, ladies and gentlemen. Okay, so numbers here, this becomes 3, right? This whole chunk becomes 3 when I plug in the numbers. So I get IL is 2 amps. So this is initially 2 amps flowing here. This is my IL of 0 minus, right, is 2 amps. If I want to do a KCL, I could solve for I. If I know initially this is 3 amps and this is 2 amps, well, that's going to be 1 amp. So I have 1 amps initially flowing through here, and I have 2 amps initially flowing through there, okay? So my I of 0 minus is 1, my IL of 0 minus is 2, and I know from my transition conditions, my IL of 0 plus is still 2. That's my bridge. That's information that's going to be useful in solving for one of those unknown K1, K2, and S's. Okay, the transition condition here. So we're going to hold on to that piece of invaluable information. Okay, so then let's go over here and draw our intuitive plot for after when the switch opens. So when the switch opens, I still maintain my current direction, but remember this voltage is going to act like the battery and keep this going. Okay, so what do we have? IL is going to do what? It's 2 amps, and then it's going to spool down, right? Water wheel, it's got spun up, 2 amps, spools down. Okay, what about the voltage? Voltage is going to be 0. All of a sudden, bang, it pops here, and then applies that pressure to keep that going, but then also spools down. The current in here is going to be initially 1, but what is this current going to do? It's 1, and then immediately after this opens, well, by KCL, I equals negative IL. It's just the opposite of this. So this is your intuitive plot following the second step of that process, right? We found our bound. All this was here, all this analysis was to find the boundary conditions, right? The boundary conditions of step 1 in our process. So all we've done is step 1 and 2. Okay. All right. What's step 3? Now we apply our KVL, KCL, Ohm's law to find that first order differential equation. Okay, let's do that. So KVL, what do? We can apply some dummy variables, plus V3, plus V2 plus VL equals 0. Ohm's law, V3 equals ILR3, good. V2 equals ILR2, good. And our inductor VL equals L DIL DT, good. Notice I chose one. I didn't choose I chose IL. So don't mix your I's and IL's so that when you get to your first order equation, you don't get a confusion. So I even say that here. Note IL only, do not mix I. Okay, it would be, it would totally work to have I, like VR equals negative I. But if you have ILs and I's and you try to do your first order differential equation process, so let's say this was an I and this was an IL, it would not work. You need the same variable. So if you had everything as I, that'd be okay, or everything is IL, that's okay, but not mixing both. All right, good. We see this as our first order differential equation. We have a variable and its own derivative. You apply the guess, so that's the next step on the process. So if you want to just, when you're doing these problems initially, you just have this kind of process next to you, that's fine. So now we go, okay, got it. What's next? Okay, I is this, DIDT is this. Okay, so we write that down. Okay, what's next? We plug it in. Okay, plug it in, good. So I'm going to plug it in, great. Okay, once I plug it in, what do I get? I get this equation here. All right, what's the next step? Okay, so I go here. Oh, I got to find with and without EVST. Great. Okay, so I look at here and I go, what are the equations? What's the equation with the EVST and without? So with EVST, it's K1 times this and LSK1. K1 times this, LSK1. Okay, great. So that allows me to solve for S. Look, the K1s cancel. That seems to be a recurring theme. The K1s cancel and I solve for S, and I get negative this divided by L. Good. What about 2? Well, I have K2 times this. Oh, I think it's going to equal 0. Yep, K2 equals 0. Great. And then I can use my boundary conditions. IL was 2 amps, not 0 amps. So 0 and 2 this time. Okay, so this is 2 and this is 0, but e to the 0 is 1. Okay, so K1 is 2 amps. That's great. So the current IL, when I plug everything in, is going to be this, 2e to the minus RL plus R2 over 2. Okay, I can plug in the numbers for R's and L's. I get negative 45t, and I can plot that. This looks like a thing that starts at 2 and then decays down to 0 with this negative exponent. Nice, that matches our intuition, yes. What about the time constant? Time constant is, if you recall, the time it takes to get to 1 over this. So this is going to be about here, right? And so it'd be negative, or sorry, it'd be 1 over 45, okay? All right, so during that switch open time, remember from KCL, the current here is actually the opposite of the current there. It's a negative IL. So all it is the flip. Perfect, okay? By the way, what is 1 over 45? It is 0.02 or 20 milliseconds. Okay, 0.02 seconds or 20 milliseconds. Okay, now again, the next question might be, well, it looks like you found IL. It looks like you found I. It's just the opposite of this. What about V? And we can say, well, V is equal to L DIL DT. Okay, well, that's pretty straightforward. To take the derivative of this, that's not too bad. We just do negative 45 times 2, right? Okay. And so this should be negative 90. Okay, let me just put here. I kind of changed the numbers in my example. I added a little, instead of 4.5, I made it 45. So this is actually 180, and this is 180, I believe. Okay, all right. Let's double check that I did all this correctly. Yep, I think that looks good. That looks good. That looks good. Okay. So again, the time constant is 0.02 seconds. So let's go to the simulation and see that we're getting the same result. Okay. What do we have here? Go to Zoom, new share, and there it is. Okay. So now this is the next example. I'm going to run this. And so we can see that the current in both the inductor and the resistor here, this R6 resistor, are steadying out. And look at the current. See, it does take some time to steady out, and this goes to 2 amps and 1 amps. And this should be 3 amps in here in the source current, and that's what we proved in that steady state condition, if you recall. Okay, when this opens up, what happens? The left side is completely disconnected, and now these two currents will be the same but opposite, and all this extra current is going to disappear through these two resistors. So ready? Bang. Okay, great. Notice how we see this jumps to -2. This 2 amps drops down, and we get this large jump in voltage stop here. Okay, so we see this nice dump in voltage. Okay, all right. I hope this this lecture helped build the intuition. We have this current fall off. We have this voltage go the opposite way, act as a battery, kind of when this, and then decay off. And then we have this current here on the R6, match the opposite version of this current. Okay, I will post the links to both of these simulations in the description, so please check those out. And I'll see you in class. All right, take care, everyone.